All right, so we're gonna talk about spin, and we'll start with, but first we're gonna start with the solutions to the previous exercise. And again, this was the roadmap we were taking, and I guess the problem was this one, where we were computing the probability of this quantum coin system, given this Hermitian operator with delta. Yeah. So the roadmap that I gave you was solve the Schrodinger equation, exponentiate the matrix using these 3 steps, simplifying, and find the probability. So I'll just take you through the steps. Hopefully this looks familiar to you, and we can go through it fairly quickly, but at any point if there's any questions, please let me know. And so I assume that everyone got to this point. This is what I mean by solving the Schrodinger equation. You can just take the exponential of the Hermitian matrix, but in that format, it's still not clear what the probability is. So you actually have to take the exponential of this Hermitian matrix, and you have to do it explicitly. And to do that, first I find the eigenvalues. I find the eigenvalues using the characteristic equation for the matrix, and in this case these are the eigenvalues that I got. And going through the room, this is the eigenvalues that I saw that everyone had. And then once I have the eigenvalues, I find the eigenvectors by solving this differential equation. I guess this is, yeah, I'm labeling the eigenvalues by the plus or minus here. So the eigenvectors are going to be plus or minus. And so I have this system of equations, and then I look at the first equation, and that's going to give me V2 in terms of V1. And then this, by just looking at this system of equation, and then also requiring the normalization condition, which is V plus minus 1 squared plus V plus or minus 2 squared is equal to 1. Then I actually introduce the square root, and I choose V1 to be just 1. So and then I could potentially multiply all this by a phase factor, but it's not going to change the computations, and I like to keep things real. No. Oh, anyway. I heard it after I said it. But anyway, so I have my eigenvectors, and with my eigenvectors, I can now diagonalize the matrix. And here, this is really just V plus and V minus. So this is how I obtain this U matrix to diagonalize my H matrix. And in particular, this means that I can write my H matrix this way, which, again, I'm pretty sure I saw everyone get to this point. And now I'm gonna take the exponential of the matrix. Here, I bring back the IT over H bar term, and I distribute it inside the diagonals of the matrix in the middle. And that's important because we want this to be actually inverses of each other. So I take these numbers and put them in here. And the result that I have is that my eigenvalues are going to be lambda 1 given by this term and lambda 2 given by this term. And by what we discussed in previous lectures, taking the exponential of this matrix then becomes the product of these 3 matrices, where we have this matrix coming from U and U dagger, and the exponential of this matrix, lambda, which is this one, is going to be just the exponential of each entry. So up to this point, we're good, right? sure that I think I saw everyone get to this point. How about, but we still need to find the probability. We've exponentiated the matrix, but we still need to find the probability. And in particular, the solution now is that the wave function at time t is going to be this exponential times the initial wave function. And here I take the initial conditions of my wave function, 0, 1. And again, we have that h I represented as 1, 0, and t I represented as 0, 1. So in here, I'm plugging in my wave function to determine my initial conditions to determine my wave function at time t. So I start by just taking this product first, and then I take this product next, and then I take this product next. And I obtain this result, and I have this as my wave function at time t. Now, I wasn't sure. This is, I think, where we started running out of time. So I'm not sure if everyone got to that point. But this is, once we exponentiate this matrix, and this is how we determine the wave function at time. Oops. Whoa. This is a minus, and this is plus. Minus and plus. And I still need to simplify. Part of this simplification, the probability that we are at tails in time t is going to correspond to this coefficient. And we still need to simplify that using the formula that we have for lambda 1, lambda 2. So that's what I do. First, I explicitly write lambda 1 and lambda 2 up here. The next thing is I factor out a common term, this e to the I delta over h bar. And this is just going to be a phase factor that's not going to affect the probability of my system. So anything, an overall factor of e to the I real number is not going to affect my probability. So that's why I factor out initially. And then I'm left out with these terms in the coefficients. And using the identity e to the I theta is equal to cosine theta plus I sine theta. I think this is called the Euler identity. We'll have to double check that. But using this identity, I can go from these exponentials to the sines and cosines. And at the end, what I obtain is that the probability of being in the tails state at time t is the norm square of this coefficient. The norm square of this times this, but this has norm 1. So it's just going to be cosine squared of t over h bar. Any questions? You?
Isn't there a factor of I in front of the sine function? Because when I got this part, I found there's an I in front of sine.
Possibly.
The expression for sine in terms of complex exponentials has an I.
Yeah, it's over 2i.
Over 2i.
I want to change
All right.
probability, but
Yeah. Good catch. So we would want an I.
Yes.
All right, great. Yeah, I didn't do my, yeah, and it makes sense because in here you have this I in front of it. Yeah, so I wasn't being that careful, but as someone else pointed out, it doesn't change the probability. So I got lucky. Any other questions? All right, good. So I want to take a second to interpret this result and what it means. for our system. So in here, this is a sketch of the plot for this probability function. So in here, at time 0, I start at 1, probability 1, because that's where we started. And then we start oscillating between 0 and 1. And the probability for tails, we can, since there's only 2, for heads, since there's only 2 states, is equal to what?
Sine squared.
Yeah. Sine squared t over h bar. So the probability of heads is all gonna oscillate. So this quantum coin is gonna be oscillating between heads and tails. And then the period is gonna be dependent on h bar. So you can see here that these periods are gonna be, the width of the periods are gonna be h bar. So the question is, what happens when h bar goes to 0? Intuitively, or from physics point of view, we should have that when h bar goes to 0, things become classical. And I want to reconcile this with this result. So the question here, if we're just looking at the graph, what happens to the graph when h bar goes to 0? It contracts. So when h bar goes to 0, as h bar goes to 0, it starts oscillating faster and faster. And how does that sit with you? Does that seem like a classical thing?
In the limit.
In the limit? What's the limit?
Goes to the average.
Goes to the average. All right. That's actually right. And but it's a little bit subtle. It's delicate the way that it goes to the average, because point-wise, it's not going to go to the average. Or if you look at the limit as h goes to 0, if you just look at a specific point, it's going to keep oscillating between 0 and 1. And in that case, the limit's not going to exist point-wise. So we need to think of a different type of limit where it actually goes to the average. So this remarks more explicitly. So if we look at this limit as h bar goes to 0 of cosine squared, it's not going to exist point-wise, PW, because it's going to keep oscillating between 0 and 1. But the claim, which Alberto made was that it's going to go to the average. And the average in this case, it's going to be 1/2. And explicitly, the way that I write this mathematically is that if I have a function phi, which is compactly supported on R, meaning that my function is 0 outside some region and then comes back up and goes back to 0. So at near positive or negative infinity, this function is going to be equal to 0. So it's going to be compactly supported. Outside a finite region, this function is going to be 0. Then if I multiply phi times this cosine square function, then the limit as h bar goes to 0 is going to be 1/2 of the integral dt. So effectively, when we're taking this cosine inside an integral, then it acts as a 1/2, as the average value of the cosine. So in this you can replace in the limit 1/2. And this is mathematically, you would say that that the limit of cosine square as h bar goes to 0 is equal to 1/2 in density, thinking of this as a cosine as a measure, so as an averaging property. And let me give you an argument for this. It's not too hard to do. It's just integrals. And in this case, for phi, I'm going to take something simple to make the argument easier to follow. The general idea is the same. And in particular, any compactly supported function, you can build it up from this type of functions. But in any case, I'm going to take, for phi, the indicator function between a and b. So I write this as this indicator function, meaning that if t is between a and b, then the function is going to be equal to 1. And outside that region, the function is going to be equal to 0. So in this case, if I take this integral, then since it's 0 outside a and b, it's the same as just having an integral from a to b multiplied times 1. And then here, I do the half angle formula for cosine squared. And I pull out a 1/2 and 1 plus cosine 2t over h bar. This integral is just going to be 1/2 the integral from a to b dt. This is what we want. And this other integral, we want it to go to 0. Or, yeah, the integral for this term, we want it to go to 0. And to evaluate this integral, I actually go to this, I actually do a change of variables. So I do the change of variables, and okay, yeah. I do the change of variables. This is my change of variables, u, and this is the differential. And then I have an integral from 2a over h bar and 2b plus u over h bar of cosine u du times h bar over 2. And the trick here is that since cosine is an oscillating function, this integral is always going to be bounded by a constant. And we have h bar going to 0. So this integral is going to be bounded, and we multiply it times h bar, and we take h bar goes to 0. And we have that this whole thing goes to 0. So in the limit, and I should have just really written this way. H bar goes to 0. In this limit, we have that it's just this term that survives, and that, and taking back the definition, then it's equal to this. Any questions? So the moral of the story is that thinking about it, thinking about the h bar goes to 0 limit, and you want to think of it as a average of the value, as the average of this oscillation, and thinking of the limit as a limit in measure or in distribution or density. And then in that case, we have that the limit is going to be 1/2. And for me, this whole example is very satisfying, because first you have you can actually compute what the probability is going to be, and it's going to be oscillating between heads and tails. And then when you take the classical limit as h bar goes to 0, you get the probability of being tails is 1/2, which is consistent with a classical coin. So if you flip a coin, the probability of being tails is going to be 1/2, and the probability of being heads is going to be 1/2. So in some sense, I recover a classical coin by taking h bar to 0. And this is why I call this a quantum coin. Any questions? Yeah.
So I'm kind of confused because before we were just like reading off, like when we don't take the limit, we just read off like the cosine function to get the probability.
Yeah.
But when we're taking this limit, we're taking an integral of the probability. And I don't know if I quite understand how they're related.
So it's the way to kind of like think about it, the way that I think about it is that taking the integral, it's an average over an amount of time. So in here I have, so taking the integral is averaging the values over a specific window. And classically, the way that I justify this to myself heuristically is that when you make a measurement, it's not going to be an instantaneous measurement. You're going to be measuring for a window of time. And in that window of time, your measurements are going to average out. So it's the way to measure something is you're not going to have an instantaneous reaction from it. You're going to take an average from a window of time. And so that's why I'm averaging over a specific window. And that's why, for me, it makes sense to take the average of this probability over a fixed window. Does that make sense?
Yeah.
Any other questions? All right. So, okay, yeah, this is the punchline. So now let me move on to spins. Up to this point, I introduced a fictitious, or a toy model rather, with the quantum coin, and it was a 2x2 system, and it was just essentially just fabricated, where everything worked out nicely. But now I want to talk about something that does appear in nature and can be tested experimentally, and this is spin. And a lot of the discussion that we've done with the quantum coin translates to this spin systems. And here I'll briefly describe what spin is. And spins are going to be properties of particles. They're going to be intrinsic properties, and they're going to be labeled by a half integer s. And we'll get into the interpretation in a bit, but the important part is that when you measure a spin of a particle, it's quantized and it can only be at certain possible values. And if the spin of the particle is s, then actually this should be greater than or equal to 0. If the spin of the particle is s, then the possible outcomes when measuring the spin measure along any direction, which we'll make more precise in a bit, is that you can only, the only possible values that you'll get is going to be minus s plus 1, all the way to s. So these are going to be quantized values that you recover from these measurements. For electrons, you have their spin 1/2 particles, and meaning that if you measure spins, the possible values that you'll get are going to be minus 1/2 and 1/2. And the way to roughly think about it, which is not quite what we did, but it's to do that the possible spins are going to be either heads or tails, or you can think of it as upspin or downspin, depending on the sign. And these are low-dimensional quantum systems that actually appear in nature. So here, I'm using this equation as my interpretation of what spin is. So in this equation, once we have spin, you can compute the magnetic moment for a spin 1/2 particle, you can compute the magnetic moment as by this formula with G unitless constant, Q a charge, and M the mass, and then multiply it times the spin, and you get you get the magnetic moment. So you can kind of think of it as a magnet pointing in a specific direction. And this would be a specific direction in 3D space. And this is essentially what spin is telling you, the way that the direction that this magnet is pointing. And the rough idea, or something that you kind of think about it for this spin, is it's also interpreted somewhat as an angular momentum. And for instance, for electrons, according to A&M, if they spin along an axis, they're gonna create a current, a circular current in this direction, and then they're gonna create a magnetic moment that's perpendicular to this circular motion of the spin. So if you have an electron spinning in space, it's going to create a magnetic moment perpendicular to this plane of rotation. But that's a heuristic explanation because this electron and the quantum particles are point particles, and they don't have a specific trajectory. So it's not like they're actually spinning, but it's somewhat reminiscent of this idea that if you're spinning in space, and you have electric charge, you're gonna create a magnetic moment in a specific direction. And so this spin is gonna be, you can think of it as a angular momentum, or I like to think of it as like a magnet pointing in a specific direction. And the way that the magnet, if you measure it in a specific coordinate, if you're in the Z coordinate or in the Y coordinate, when you measure the magnet, whether it's pointing north-south or south-north, then you only get two possible outcomes. It's either the magnet's either pointing up or the magnet's pointing down. And that's going to be true in any direction. If you measure it in the Y direction, it's either going to be pointing up or it's going to be pointing down. And in the X direction, if you measure it, it's either going to be pointing this way or it's going to be pointing that way. So it's quantized. There's not going to be, so the spin is going to be either plus or minus 1/2, and there's not going to be anything in between. So it's either pointing in one direction or pointing in the other direction. It's kind of like the flipping of a coin. Once it lands, it's going to be either heads or tails. And what I want to do is describe this dynamics or introduce operators related to this spin observable. And these are going to essentially become the basis for the quantum circuits. You're going to think of the input and output to be spins, a collections of spins. And depending on your circuit, it's going to flip the directions of the spin, and that's going to be the result of your computations in the quantum circuit. So in here, I'm going to, these are going to be, the spins are essentially going to be your qubits, your information in the quantum computers. So based on the information that we have for spins, and I'm focusing on the spin 1/2 systems where we have only two possible values, that means that we're going to have only two possible eigenvectors, which I denote by spin up or spin down. And these are going to be the two possible eigenvectors for my operator SC. And this is the spin pointing in the C direction. Yes?
In that first eigenvector equation, shouldn't they both be spin up?
In the first eigenvector equation. Oh, yeah. Nice catch. So we have this operator, which is the operator related to measuring the spin in the C direction. And it can only be negative or positive. And that means we have only two eigenvectors, and we denote these eigenvectors by these two up spins, by the by this notation of an upspin, which has eigenvalue 1 pointing up, and a downspin, which has eigenvalue pointing down. So this is going to be a particular basis that we can work on for the Hilbert space. So our Hilbert space of the system for a one spin particle is just going to be a linear combination of upspin and downspin. And these are going to be in the c direction. Part of the notation here that we'll see later is that an upspin will also denote it as a 1 and a downspin as a 0. So making the connection to classical, this would be a bit on bit, and this is an off bit. But in here, this is going to be our space of qubit, of 1 qubit, where it can be a linear combination of the on bit and an off bit. Any questions? All right. So if we choose this coordinate for the upspin, this to be their basis coordinate, so this is going to be, upspin is going to be 1, 0, and downspin is going to be 0, 1, based on this equations right here. We have that this is going to be my operator for the upspin, for measuring the spin in the c direction. So it's going to be 1 minus 1, because these are the eigenvalues. And this is also denoted sigma sub c. And for the other coordinates, we have similar operators that are going to correspond to measuring the spins in the different directions. This is going to be 0, 1, 1, 0. This is 0i minus I 0. And denoted sigma x, sigma y. This sigma x, sigma y, sigma z are called Pauli matrices. They're called Pauli matrices. And it turns out that if H is a 2 by 2 Hermitian matrix, then you can actually write H as a linear combination of these three matrices. They create a basis for the space of this 2 by 2 Hermitian matrices, where alpha is alpha x, alpha y, and alpha c are real numbers. So essentially this is capturing all the possible information that we could have from a 2 by 2 quantum mechanics systems, this spin. So these are fundamental matrices for qubits. Essentially everything is built up from this three matrices, and they're related to the spin. So in here, I just gave you the definition of the spin matrices, and I want to sort of motivate that this is the right choice for this spin matrices. I could have chosen pretty much anything from the first eigenvalue equations really pin down the SC operator, but the other two I could have really chosen anything else, and I want to motivate that they're actually the appropriate choice for the spin operators in the x and y coordinates. So this is my my motivation. It's my showing that it is an appropriate choice. It's not necessarily a proof, it's just a consistency check. So first I look at the spin in the x direction, which is given by this matrix, and I find the eigen vectors with the eigenvalues plus or minus 1, which means that if I apply the spin operator to this combinations of spins, and this is down, then I obtain this an eigenvector. And in particular, these eigenvectors of the Sx operator are actually corresponding to the up and down spins in for the x direction. And in this ones, these operators are going to be my spins in the c direction, and these are going to be my spins in the x direction. And I have that my upspin in the x direction is made up as this linear combination of, and this is down again, is made up this linear combination of spins in the c direction. So it's this linear combination, and the downspin is computed as this linear combination of c spins. Oh, wow. And in particular, if I have a state that's in the c upspin direction, then it's equal to this linear combination of x spins. And if I compute the probability of measuring my upspin in the x direction, given that my state is an upspin in the c direction, we know that this probability is given by this dot product, and this is equal to 1/2. And this is the motivation or the consistency check that these operators are the spins in those direction, because what I'm doing here is that I have a state that's prepared in this upspin direction, in the c direction, and if I want to measure the upspin in the x direction, we know that it's either going to be upspin or downspin. And in here, this is telling me, since it's quantized in any direction that you measure it, this is telling me that if I measure it in the upspin direction or in downspin direction, then it's going to be equal probability. So this upspin can either fall flat in the upspin in the other direction or the downspin in the other direction. So if I had chosen other matrix, I don't necessarily get this, that the eigenvectors are going to be equally likely from the other eigenvector. And at a completion, I did the same computation for the y direction. So in here in the y direction, I have that the y spins are written as this combination of c spins. And if I prepare the state in the upspin direction, in the c coordinate, it's going to be giving us this linear combination of up and down spins of the y direction, and then the probability of measuring the upspin in the y direction, given that we have the state in the upspin in the c direction, it's going to be given by this quantity, which is again 1/2. And again, this is consistent with this idea that it's kind of pointing in some sort of spinning in one particular direction, and we get equal probability of going to downspin y or upspin y. So this is for me a consistency check that these operators have the proper interpretation. I didn't check that this is enough to pin down those operators, but I think it is. I think requiring that this idea is that if you measure in the other direction, it's equal probability, then this is going to pin down if you have the SC and you're looking for SX and SY, I think it's going to pin it down. Might be up to some phase factor, but the phase factor is not going to change the probability. So this, for me, is again satisfying computations. I'm going to wrap up soon. So we talked about one spin, one particle, one spin particle, but we can look at collections of spin particles, and that's called the spin system. And as we saw in the postulates of quantum mechanics, if we look at a collection of different particles or different systems, then it corresponds to a tensor product of the Hilbert spaces. And here I'm looking at a system of L spins. And it's just the tensor product of this L Hilbert spaces. So it's going to be the tensor product of this C2 L times. And in this case, the basis is now, you can write a basis which is labeled by the location of the upspins. This is one particular way to denote the basis, and everywhere else it's going to be downspins. And n is going to label is the number of upspins. So this is going to be your system for a collection of spin particles. Actually, any questions? Did I ask about any questions here? Any questions? So far, so good? Okay. So this is a particular example. This is called the XXC model, Heisenberg-Ising spin 1/2 XXC model. And this is a particular example of a Hamiltonian for a spin system. In this case, I think of the spins to be on a ring of length L, and we have certain upspins along the ring, and the Hamiltonian or the Hermitian matrix is made up of local interactions of adjacent particles, J and J plus 1, and J goes from 1 to L. And if J is equal to L here, and this is L plus 1, I assume that the interaction is between L and 1. Particles L plus 1, so that's why I'm on a ring. And the Hamiltonian here is made up of this spin operators. I had a good Jeopardy question, and I guess we'll pick it up here. We'll pick it up in a bit, but if you actually look at the action of this local operator J and J plus 1, if this is the location of the if this is the configuration at sites J and J plus 1, then this is only acting on these two adjacent spin particles. And if they're both spin up, nothing's going to happen. If they're both spin down, nothing is going to happen again. And if they're opposite spins, they're going to try to flip. And they're going to have an interaction. And this is for the local interactions for two adjacent spin particles. And then you go through all the adjacent spin particles and try to run this dynamics. And locally for these two spin particles, if you write it into matrix form, you obtain this matrix. And this is actually the system that we were looking at for the heads and tails. And in particular, the heads and tails system corresponded to a two-spin particle. Oop. And up and down. So, where's my head today? There we go. So it corresponds to a system where actually L is equal to 2 and N is equal to 1. So this is the system that we actually solved for. It was a spin system of a ring of length 2, just two particles, and only one upspin. You can actually check in here that the number of upspins is a conserved quantity. When these two interact, they just flip, and so the number of upspins is not changing, so you can actually fix the number of upspins and only look at this submatrix. And then that's what we looked at. So in here, what we were doing with the heads and tails, there was a spin particle that was oscillating between these two configurations. We'll leave it here for now, and in the next class we'll do L is arbitrary and n equals 1, and we'll look at that spin system.